And then it turns out that these pulses also generalize well. So they also homogenize the flip angle for subjects not part of the database. One limitation is that these pulses are tied to the PTX call that has been used for the database, of course. So they perform very well across sites as long as they use the same call. If you have a different call, you need to acquire your own database and calculate new universal pulses. And we acquired our own database, which we call BLT database. And it's called like that because Bonn, Liège, and Trondheim are involved, which are the sites involved in the Skyfield project. And as you can see, it's already a pretty large group of large data set. And we acquire field maps as well, so B0 field maps, as well as 2 B1 field maps per channel. And we did that because at the beginning, we weren't quite sure whether the faster sequence would be good enough as a basis for PTX pulse design compared to the gold standard, which takes still almost 8 minutes. But in the meantime, we are sure and pretty confident that it works pretty well, and not least also due to the recent improvements on the sequence that my colleague Philip is presenting at this conference as well. Now, even though we don't need in the future to have these field maps to calculate our pulses for this scan session, they are so short that we can still include them. So our database will grow rapidly in the future. So with every subject that we scan, we're going to include these maps, these mapping sequences, so that we have a really large B0 and B1 database soon. What are we going to do with this? We are going to calculate PTX pulses, and there are different approaches to this, as you probably all know, and I will very briefly touch on them. So there is the KT points method, for instance, suited for non-selective excitation. And the nice thing about this, it's a relatively simple optimization problem. And what you do is you deposit RF energy at certain spots in the excitation case space to homogenize dB1. Sometimes it's not, it's limited in fidelity. There is a spins method where instead of using blipped gradients between RF deposition spots, you apply the RF along the trajectory, and the gradient trajectory is fixed during the optimization. This is great, but it can lead to long pulses. And the method that we converge to and really like is the grape method, which optimizes per time step both the gradients and the RF. And this can lead to shorter pulses with high fidelity, but it takes a long time to calculate them. But that doesn't really bother us too much, since we only need to do this once and then just apply it in the subjects. And this GRAPE stands for Gradient Ascent Pulse Engineering. And without me being an expert on that, I will be very, very superficial on that. So it's essentially an optimal control design that controls the system. In this initial instance, it controls the dynamics of the spin system, so the Bloch equations, and each RF and gradient step is varied in this optimization. So there is many degrees of freedom. To adapt this for universal pulses, we need to reformulate the cost function, which is now homogenization of the flip angle. And to make it universal, we basically just have to sum over all the individual cost functions, the subjects. But you can imagine that this increases the degrees of freedom even more. So this makes it so computationally demanding and long, but it's well suited for universal pulses. And one application where that really shows the power of these simultaneous optimization of RF and gradients has been done by my colleague Ed Pracht on last year's ISMRM, where he used that at 70 using single channel, so STX gray pulses to homogenize the contrast of the MP-range and the space sequence. And you can see, compared to the PTX universal pulse, it really works great. and much better, both of them, compared to the CP cases. The only downside is with one instead of only, with only one instead of 8 channels, for instance, for transmission, the pulses take longer. And that makes them more sensitive to off resonances. Since in this project and also overall, we tend to go more and more to PTX studies, we focus on these pulses now. And anyhow, we also need more complex pulses from time to time. So this requires PTX anyways. A good example for a more complex sequence that involved 3 different types of pulses already is this SLAP selective T2-weighted space sequence that my colleague Daniel Löwen implemented. So this is essentially a 3-dimensional turbospin echo sequence, and we have different pulses. And the approach of him is to first design a SLAP selective KT spokes excitation pulse. Then, knowing the phase that this introduces, puts this phase as a constraint into the design of the following 180 degrees refocusing pulse. And this is really crucial. And then the subsequent refocusing pulses in the pulse train are also great pulses, and they need to be symmetric, which is important to fulfill the CPMG condition. So you can see it's pretty complex, but it works pretty well, again, using universal pulses. Compared to the gold standard sequence, which is typically a 2-dimensional turbospin echo sequence, we have thus homogenized the cerebellar contrast and signal, and also the SNR has been improved quite significantly. And also it turns out that the 3-dimensional SLAP space is less motion sensitive than the TSE. So summing up the anatomical sequences that we have developed in the project, or in the 2 projects, we have the MPRH with universal pulses with or without water selective excitation and inversion. It features also more techniques like elliptical sampling and caipirinha. Also, you can have multiple echoes or 2 inversions if that's really needed. And the space sequence, as I said, has either non-selective or SLAP selective variation. And also it includes a T2 prep inversion, so that we have a fluid attenuated inversion recovery sequence flare. Both of them share features like external flash autocalibration scans to reduce motion sensitivity and also to cut down scan time. And optionally, they can also perform compressed sensing, sampling, and online image reconstruction. And to show you that this works pretty well, we did a comparison study where we compared the 0.6 millimeters isotopic protocols that we set up with vendor protocols with the same acquisition time. And even though these images have been bias field corrected for receive field sensitivity, you can still see that there is significant improvement in the contrast of the cerebellum, for instance, and very clearly you can see in the space and the flare images that these issues have been resolved with the universal pulses. And this not only works in single subjects, it works across the range of various heads, small to large. And not only in a flare, but also we see substantially improved SNR in different regions of interest across the brain, and also improved contrast to noise ratio or absolute contrast, and reduced signal homogeneity. But you may ask, the BLT database is collected on healthy subjects, so the universal pulses may not perform on patients, or do they? Well, so far they worked on patients pretty reliably, and more than 100 patients have already been scanned with these protocols. The only times when the scans didn't work out well, it was rather due to patient-specific motion and not B1. These are some other patient examples having all contrasts put together. And there is also new contrast shown here, like the CEST contrast on the right, so quantitative map, and also the SWI images shown here. And this is what I'm talking about next, because we also consider this like a structural imaging method. In contrast to the other sequences, we based this on our custom sequence, which used this skipped Kuiper sampling. So it's an adjustable EPI factor combined with Kuiperinia sampling, with or without blips in slice direction. And it also features some tricks to mitigate artifacts that can happen but don't have to happen, and many more features. It's available if you want to have it. The PTX version, that is really important to have the pulses that Daniel again implemented, especially having a water selective universal pulse. And this is extremely vital for the quantitative imaging that we do with this, but also for the structural imaging, it is really handy. So why would we do structural imaging with 3D EPI in the first place? It should have lower SNR compared to the gradient echo imaging, for instance. Well, yes and no. Yes, if we increase the bandwidth to have short echo spacings, that will reduce SNR. But it is still enough SNR, depending on the voxel volume, of course. And we need typically long TR in the order of T2 star. And if we have small voxels, large matrix sizes, the imaging would otherwise be extremely long if we take a gradient echo imaging. So the EPI factor is very well suited to accelerate and to increase the SNR efficiency. And this is because of the long TR. We can show that analytically, and I don't want to bore you with this, but some simple assumptions, and it turns out that the optimal TR that maximizes this SNR efficiency is at relatively long TRs, and we can use that to squeeze in as many EPI readouts as fit into this long TR. If the SNR is not sufficient, well, then we just average. This has some benefits because having a short acquisition per volume also means we have little dynamically induced artifacts, such as due to motion or field changes. And this is our workhorse SWI QSM sequence that is shown here at the bottom. So within 5.5 minutes, we acquire 0.4 millimeters isotropic across the whole brain. And at the same time, with the same parallel imaging, we could only acquire a small portion of the brain using the product GRE sequence. Or if we would acquire the same volume, it would take 34 minutes. And this has been applied also already in many, many subjects in our lab since 2 years or 1.5 years. And I think Theodor Huber is going to talk a little bit more about this. But having done this, we were asking ourselves, how far can we even go? Could we even go below 0.4 millimeters resolution? And especially having the 11.7 Tesla scanner in mind. And we just tried, and it turns out it is in principle feasible. So we got 0.2 millimeters isotropic nominal resolution in less than 40 minutes. So that means it is within a single scan session, which is really valuable. But it involves averaging. And interestingly, the sequence that we used here also used this universal SLAP parallel transmission pulses that were originally designed in this project for fMRI. And it's also already used for fMRI. And with this sequence, we also already got the first preliminary results ex vivo at the 11.7 Tesla. And we hope to optimize this for this purpose in the very near future. Already summing up, I've talked about the universal pulses concept that we followed in the protocol, in the project, especially the GRAPE pulses and the BLT database. We have developed many sequences for structural imaging. I did not have time to talk about all the quantitative applications that really benefit from these pulses. And also we have more works in progress. For instance, like my colleague Martin Feldman introduced today here at the ASMMB, multiband GRAPE universal pulses, and also having a larger B1 and B0 database soon available. Of course, we also think about making universal pulses for subpopulations, perhaps depending on head size or other parameters. Then also we are porting the sequence to the newer scanner generations, and even though not really related to the universal pulses, we are also working on prospective motion correction with servo navigators. And with this, I want to close, thank my colleagues and the involved teams, and I want to close and thank you for your attention.
Yeah, thanks, Rüdiger, for this great talk and overview over this somewhat fascinating arsenal of sequences you've implemented now with full PTX support. Are there any questions? Oh, Moritz, go ahead.
Hey, thanks for the great talk. In the textbook and in my courses, I tell the students EPI has a lot of distortions artifacts. I don't see any of these in your images. So what's your magic?
Yeah, so that's true. If you use typical protocols that have a pretty long readout for the whole case space. Now, what we typically do is we have like a very high segmentation. We apply parallel imaging and segmentation to be very fast. So the phase encoding bandwidth, which is the relevant factor here, is actually pretty comparable to typical gradient echo readout bandwidths. Therefore, the distortions in the phase encoding direction are pretty comparable to geometric distortions that you would have with a typical gradient echo acquisition. Yeah.
Anything else? Any more questions for Rüdiger? Well, I have one for you. I mean, how many of you are working on a Siemens system with PTX support in the Nova coil? And how many of you have actually used those sequences, which are clearly out there and capable of making nice images? 1, 2, 3. Well, that's not so bad. That's a start. Spread the word. It's good stuff. Thanks, Rüdiger.
Okay.
There'll be more opportunity in the wrap up to ask questions afterwards. He'll be back. He has to rush off to give another talk elsewhere. Anyway, we're moving on to a talk by Theodor Rüber. He's also from Bonn, from the University Hospital. He's a neurologist and head of the Translational Neuroimaging Group, if I'm not mistaken, working in epileptology. I think he's not directly affiliated with the AROMA project, but I think he has been dragged here as a fantastic example of how close collaboration between sequence developers like Tony and users actually on the clinical side actually leads to sort of some perspectives that we're about to hear about. Thanks, Theodor.
Well, thank you so much, Benedikt and Tony, for the invitation. Hello, everyone. I'm Theodor, and it is great to be here. This is my first physicists meeting, and I hope I won't say anything wrong. If I do, please correct me. So we have the privilege of working with Tony and his group in Bonn. This is my group, and this is basically the campus. We are in that building over here. That's the neuroradiology, that's the epileptology, and this is where Tony and his group is. And I'm showing you this because this is somehow also how we work. So we work between those fields, clinical, epileptology, neuroradiology, and then we are happy to be able to apply the sequences that were just proposed to some of the patients. And what do we do? So we use the scanner, first of all, as a powerful tool for neuroscience. And then second of all, we try to leverage this double role that MRI has as a powerful neuroscientific tool, and also as, of course, an unique diagnostic modality in clinical neurology. And the idea is basically, and this is why it's called a translational neuroimaging group, to find insights about the brain, about also its pathology, using these scanners, and then translate them to clinical grounds and use them there for better diagnostics. And I think I found a few of these insights that I would like to share with you today. When Tony and I talked about this meeting, he always said that epilepsy is supposed to be a killer application for the ultra high fields. And I'm hopefully can show you now why this is the case. So in epilepsy, you have basically two ways to treat patients. One is by pharmacotherapy, so you give them drugs, and then 2/3 of them will be seizure-free. And the other way is, if that does not work, you can try to find a lesion and operate these patients, if you know where the lesion is, of course. And these lesions can be very subtle. So here's an example of a lesion. You may not see it. It's very easy to miss. This is a focal cortical dysplasia. It's a migrational defect, so it's happens during the embryonal stage in the womb. And it's very likely to cause epilepsy, but it's very small, so it can be really well resected. And if it's successfully done so, then the individual will be seizure-free afterwards, so will be cured of epilepsy. And this is how a post-surgical result will look. Most of the times, these surgeries won't cause any deficits, but only 1% of these people who cannot be healed with drugs undergo surgery. And why is that? I mean, there are many reasons to this, but one reason is because we cannot find these lesions. And that is, I think, what Tony means when he talks about these killer applications, because we hope that not only we as physicians, but also our patients cherish, is that the ultra-high field will be able to localize these lesions. It is, of course, not as easy as this, but I'd like to show you how we try to use 7T to diminish the number of people that cannot undergo surgery. You can see here that these are the drugs. I like to show this because it's very obvious that so many drugs came into the market over the last 40 years and they've been prescribed. And but the summary is of a big meta-analysis is that this has not really changed the amount of people who got seizure-free. Well, if you look at MRI, you see that over the same period, the inconsistency between what has been found in MRI and what then was found in histology, so as we say that the ground truth of that this got better every year. And this is, of course, by the advances of neuroimaging, which in our view lay on 3 pillars. And one of these pillars, of course, the MRI hardware, then the sequence development, then the post-processing, which may be used, and then, of course, also the diagnostic capabilities of the radiologist, and maybe also of AI algorithms. And we'll look into all these things now together. So if we say diagnostic capabilities of radiologists or of AI algorithms, what do we mean? And I think that's very important with regard also to the ultra-high field to highlight this. There are different capabilities that we mean. First of all, the question that may be asked is that of it's basically a detection task. So if you want to localize a lesion, that is a detection task that's is being asked for. But there are also other tasks. There is for example, segmentation, or there's classification tasks. And you cannot per se say that 7T is better than 3T if you do not name in which of these domains, basically, right? This is something that has not really percolated through the neurology community. There are guidelines on how to use 7T in epilepsy, and they lay on the experiences of almost 2,000 patients being scanned worldwide with epilepsy. And they don't really give numbers, but they say that using 7T, this will has a diagnostic advantage of 1/3 maybe that you can diagnose based on the 7T. Well, we have looked into this in one, and this is one example that I'd like to show you. This is such a male patient with an FCD, so with this migrational defect, and that's the one TEFLA sequence that you saw earlier in Rudia's talk, and this is the flare. Here in the flare, you have to know is the most important sequence for us in clinical epileptology. And if you look really closely, then you'll see that there is such a lesion, and that lesion indeed was missed on 7T. I'm going to rewind here. There it is. So, wait. Yeah, that's the lesion. And that was not found in 3T. But if you now go back to the 3T image, you will see it there. So the question is, was it missed because the radiologist was sleepy, or was it missed because the image, the 7T, was really better? So I've brought you some other examples, and here also you see, for example, the hippocampal sclerosis, which is a very common cause of focal epilepsy. You see some ataxia, and you see these differences here. And this is a healthy control, and this is this patient with ataxia and the cerebellar peduncle, where you see an asymmetry. And that's also the slide that Rüdiger showed before with the angiopathy and glioblastoma. But the question always arises, is this, I mean, it's beautiful images, of course, and it's very obvious what this patient suffers from, but is there really a diagnostic advantage over 3T? So, and how do you measure this? So this is an example I found where I think this is very, very obvious how it can be measured. And the metric that is used here is the length of the vascular tree that you see down here. In the second line, you see that the vascular tree is almost 30 meters long in a 70 and only 14 meters in a 1.5 Tesla, right? But then again, the question, does this really lead to radiologists finding more lesions or better describing them in 70 as compared to 1.5 T? So the first thing we have to really do if we want to come up with any estimation about how well 70 performs is that we have to come up with metrics and that we have to compare to 3T. And this is the same hippocampal sclerosis that you saw before, but here now compared with 3T. This is exactly what we do. And you see that you can, the internal architecture of the hippocampus can be better estimated, evaluated in the, oh my God. In the 70 over here. These are some other comparisons between 70 and 3T. So this is one example. I'd say it's really hard to see anything in 3T. So this patient suffers from nodular heterotopia. These are basically parts of the cortex which on their way from the ventricles to the cortex got stuck in the middle, basically. So this is how the brain develops. The cells start in the ventricle, and then the cortex unfolds, and sometimes cells get stuck, and then you have heterotopias, which are not dangerous, but which can also cause epilepsy. And you cannot really see them here, but you can clearly see them here. So that's, I'd say, a big advantage of 70 in this regard. And then also you have another example with a double cortex. So you see here, for example, a second cortex just below or beside the normal one, which is also highly epileptogenic, and it's also very difficult to see in the 3 Tesla. But there are other pathologies, for example, cavernoma, which is some kind of tumor, where you wouldn't really need 7 Tesla to look at it. So this you would see in both under both field strength and 3T and in 70. The same goes for this tumor. This is also an embryoblastic tumor that you see also under 70 and also under 3T. How about the AI algorithms? Do they perform any better under 70? That would be another hope that could be cherished. And there are plenty of those algorithms being published every day. For example, this one under 3T, and they claim that their model detects 61% as compared to human performance, where the human performance was at 0. But now if you look at some of the cases that present, you see that the lesions that they describe can be seen really on a small thumbnail. So it's probably the performance why it was 0 is why because this was evaluated by the authors themselves, were not radiologists, right? So this is something that, and of course, I don't want to blame them. I just want to show before you try to show the diagnostic superiority of any modality, maybe 70, 3T, or any algorithm, you first have to define the baseline, and that's not really what has happened also with regard to 3T or to 70, because we don't have the right metrics. And let me show this point now here. So this is also one of these 3 of these algorithms that try to automatically detect these FCDs, these small little lesions. And what they count as a lesion being found is if the prediction has a 1 voxel overlap with the ground truth. right? So that could mean this, which would be helpful. This could mean this, which may even also be helpful, but this could also mean this. And some of the algorithms are so smart that they just basically define the whole brain as a lesion, and then they find it every time, right? You know where I'm going, right? So the problem is that we haven't really defined a baseline. If you want to compare it, we have tried this in Bonn. We have had 30 human raters and 3 algorithms which looked at the same data sets, and then they had to say, well, there's a lesion there, there's a lesion there, and we have done that at 3T. And the next step, of course, is that we do it at 70. And you see that, and that's so important, that the human performance varies so much. So neuroradiologist finds 3/4 of all lesions, right? So this is the peak performance. It's the head of the neurology department. And then epileptologists finds 2/3, right? And then neurologists, only half of them, psychiatrists, only half of them. General radiologists do not perform so well, right? Because they don't look at brain so much. And then there are also others, basically, I mean, here I can say it, at home I cannot say it, but these are basically neurosurgeons, and they perform worse, right? So, and now the next step is that we repeat the same thing under 70, right? And if then rates are up, if they increase, then we may claim that there's really in this domain, in this lesion detection domain, that there's an advantage of the ultra high field, right? Here we have started with this, so we have applied different algorithms for lesion detection on the same 3T and the same 70 data set. And we can see that only 2 of the models find the lesion in the 70, so they find it more in 3T. But here again, does it mean that 3T is better? No, it only means that this algorithm has been trained on 3T, right? And that may go for the radiologists themselves as well. So they only perform. They may perform. So the reason why they do not perform better at 70 is not because 70 is not better, but because they're just not used to looking at 70. If they were, then they would find more than 3T, or we don't know. But that's exactly what we have to test. And that's what happens right now in Bonn with the data set that Rüdiger was talking about. So we make the radiologists go through all these images, and we have them not, so the contrast is not 70 3T, it is 3T and 3T and 3T and 70. Because if we don't do that, then people say, well, it's only because they looked at 2 images, right? 2 different images of the same patient, and that of course enhances diagnostic sensitivity. So we really have to contrast 3T versus 3T 70, right? So these are all the things which I think are very important. So what I say we have learned so far is we need standardized evaluation criteria for 70, for 3T as well, for all imaging, and we need open source data sets for 70. And that's something that we're working on in Bonn as well with Tony's team. And we have published all these lesional data sets under 3T, and you can download them and use them for training. And we're planning the same thing for 70. Let me show you one example of the QSM application that Rüdiger has talked to you. So I talked about all these lesions causing epilepsy, but of course the pathognomonic symptom of epilepsy is epileptic seizures. And we have not been able to visualize them so far, but that would be really interesting, right? If you had a patient and then he or she had a seizure, and then you put him in the scan and you say, well, that's where the seizure is. And you may try to sensitize the MRI signal to different structural underpinnings. So some of them really were in the scan 45 minutes or so after they had a seizure. And that's a unique view, basically, in the brain, and a view that necessitates 7 Tesla, because you're not able to show this this very small, subtle difference in susceptibility under 3T. So what we have been thinking about in Bonn is we've read all of your papers, of course, not all of them, but many of them. And we try to think about whether what you found out with regard to the SNR, for example, also goes for the diagnostic validity, right? So is it really like this, that the diagnostic validity is a linear or supralinear function of the field strength, right? And how do we find this out? I used to think as a naive neurologist that the future only belonged to higher field strength. But if you look, and that's my second research interest, if you look at how unequal the access to MRI is worldwide, and if you look at I think it's approximately 120 machines under 70 that operate worldwide, then it's pretty clear that this will not be open for most of the people in the world, the 70. So how do you deal with this? And we've done some research on this as well. We had a ultra low field system, the hyperfine that you may know, and we have scanned people also in the hyperfine system, and the images don't look so bad. But why am I showing you this? Because we try to come up with so this, for example, the same patient that you saw at the beginning with the FCD over here in the 3T, and you may also, well, you don't really see it, but you could assume that it's there in the ultra low field. But why am I showing you this? Because that's what we try to establish. We try to come up with a function that shows you how helpful which field strength is for which of the clinical necessities. And with regard to the inequality, that you have a triage system at the end where you say, well, definitely not everyone who needs an image needs to go in a 7T. What are the cases that need to go in the 7T? What are the cases that can go into the hyperfine, in the ultra low field? And what are the cases that may have a 3T? And there's definitely big value of the 7T as we find it in epilepsy. And I'm telling you this because I think it's maybe paradigmatic for or generic for other pathologies as well. I think this is a really interesting use case in epilepsy. So the idea is that we use this case in epilepsy to maybe create a more equal access to different field strengths, and that we use more the downsides, the advantages of it, and maybe also that this helps us to steer clear of the disadvantages. So with this, I'd like to thank in particular Toni Stoecker and Rüdiger Stirnberg, of course, not Toni Stoecker, sorry, and I thank you for your attention, and I'm looking forward to your questions and discussions.
Thank you very much, Theo. Are there any questions?
So maybe this is not a question to the clinician, but to the people who make the methods for you. But you're all here, right? So about these epilepsy lesions, isn't there some features that we could optimize for, right? They have a certain sharpness, a certain feature in the image space that we could optimize sequences for. Is there any way to make only them bright and everything else dark?
I'm not so sure how similar all these lesions are in your case. So if they are very similar, of course, we could try to account for that in the development. That would be actually something for you to do, Moritz. I think this is exactly your topic.
If I know what to look for, but that's the question, right? Did you ever run like different kinds of variable flip angles or echo times, and is there like a better sequence to spot these or worse sequence to spot these? Is there any experience on that?
Not yet investigated. Thank you. Any questions for the clinician?
Yeah, but I think it's really an important point, because we always assume that the only value of or that the main value of the field strength is the high resolution, but that of course is not all of it, right? So this is what I try to differentiate between detection, where resolution is probably the most important feature, and then segmentation and classification. And for classification, probably resolution is not the most important thing. Probably it's other metabolic imaging, for example, for classification is more important, and that of course highly profits from higher field strength, right? So I think we shouldn't really, in the clinician's mind, it's just reduced to, well, it's a nicer image, it has a better resolution, so it's better. But that's of course not the real value of it, at least to my understanding.
There's one more question.
We still have time.
A quick question, please.
A quick question. I'll be quick. Thanks a lot. It's really interesting to see the clinician's perspective of how to put this added information to work. It prompts me to keep wondering to which degree the added information that is available technically, these higher resolution, higher SNR images, will ultimately basically over-challenge the human viewer of the images. To which degree are we now rate limited by how much people can see versus how much information we can physically put into these images?
Yeah. Oh man, that's a very challenging question. I mean, what we see is so for example, now with the AI, the cases in which AI is helpful is not necessarily the cases in which they find lesions better, but because they were complementary to humans, right? So the best radiologists found 75% of all the lesions, and the AI algorithms, the best AI algorithms did too, but they found other 75% of the lesions. So that made the clinical value, right? So not that they could do it better, but that they had a different approach to this. Well, but I'm aware of the fact that this doesn't really answer your question. I don't know. We will have to discuss it, I think, after the session.
Oh, we have 3 more days to go.
Yeah.
Thanks a lot.
Thank you very much, David, too. Well, coming to our next speaker, Malte Riedel from ETH Zurich, talking about motion detection and field sensing at ultra-high field.
Hi, everybody. Also, warm welcome from my side. And I'm very happy for this talk just before me. Like, it provides already half my motivation because there's all this stuff where we need high resolution and, of course, motion correction. So I'm happy to give you my and our take from our group on this topic. So that way. Okay, I would like to start with 3 examples that should give you a feeling for the problems at hand. PMC in this presentation is standing for prospective motion correction. So that is a process of the scanner adapting the scan geometry in runtime. So during the scan already, so that you directly get out a corrected image. So in the left image, you see a head motion case, PMC off, nothing was done. We see the usual blurring. So frontal lobe is basically gone. And of course, the attainable resolution is limited by such effects. And we are targeting this often in high field imaging. And therefore, this is kind of a must if we do such methods. But even if we do motion correction and we do it well, the rigid motion is well resolved. Like, for example, in this case, we see the interhemispheric fissure clearly. But there are smearing effects here. There's an arm motion happened, a strong one to be true. And in this case, the head was moved and the field inside the head has changed due to that, leading to this shading artifact over the ear canals. And by like these effects, they become relevant, especially for high field and high echo time imaging. So stuff like QSM, like fMRI, T2 star weighted imaging, but you can also, depending on the parameters, have them in structural imaging. So they become relevant at high field. And especially underlying these 2 cases, like they are both field related, but the things that are causing them, one time the arm, one time inside the head, they have a very different spatial structure and they need a different treatment. And that makes up already the agenda of my talk. It has basically 3 main points. First, I would like to talk about the servo navigation approach for runtime rigid motion correction. So the left image, what do we do about the rigid motion? Then an expansion to runtime gradient shimming. It's about the arm and post-dependent field-corrected image reconstruction. That's about more spatially complex field changes in the head. So starting with the servo navigation. It's a navigation method. We basically need 3 main ingredients for that. We need to insert a navigator into the sequence. We need a model to estimate parameters. And the third one, we need to have an adaptation, like a control circuit, to apply this to our scanner. I want to go through all these steps one by one and then show you some results. So this is a standard 3D gradient echo sequence where we insert the navigator between the SLAP selective excitation and the imaging gradients. And like you see this wiggly sinusoidal shapes there. It takes about 2 to 3 milliseconds usually what we do. On the right, you see the K-space trajectory that this is following. We acquire 3 orbits coming from the K-space center out on a radius of usually 400 radian per meter, and then driving around the 3 orbits. This is quite good to capture rigid motion for several reasons. Actually, the method I'm going to present on the next slide also works for other trajectories, just as a side remark, like spheres, helices, and so on. But we find this one quite good. This is now the model, the second ingredient. So it's a K-space model. We model our signal variation with respect to rotation, shift, global phase, and frequency, things that usually can change during a scan. So our current navigator signal S-curve with its trajectory, referring to a reference navigator S-ref in this way. And we use and exploit Fourier relationships in this K-space image. So rotations in image space are rotations in K-space. So we have a rotation operator on the trajectory. The shifts in image space are, by the Fourier shift theorem, are K-space ramps. That's what we see here, phase ramp. And global phase and frequency changes are just multiplications of phases in K-space as well. So there we have our model. Now we linearize around the reference point in time. So we pick one reference navigator in the beginning and say that's the center of the universe. And we model the difference of current navigators to that reference navigator with respect to the parameters we're interested in through a linear matrix that covers that contains the derivatives of the signal with respect to these parameters as the columns. And it turns out that for 3 of those parameters, the shifts, phase, and frequency, you can analytically just derive them from above, given the reference navigator. So it's just for the shift, for example, IK coming down, IK as ref. There we have it. For the rotation, it's harder because with rotation, new signals are entering into our sparse navigator trajectory in K-space. We don't know the neighborhood always. And for this, we apply a finite differences approach. We measure 3 further navigators in the beginning and just by finite differences, basically approximate the derivative by measurement. And finally, we have the matrix we are estimating via linear least squares. So that's what we do. And now we have the last ingredient, that is runtime control. Normally, you would just sit down at your host computer, one way, set the scan geometry, scan, and that's it without prospective motion correction. What we now do is we start the scan, and after the dummy scans, we acquire several references in just a few hundred milliseconds, like really quick. We send them over to feed the linear model and set it up. And afterwards, every incoming navigator is evaluated by the model. We get out parameters and send them back to the scanner to adapt the gradient rotations, the RF, and the demodulation. And doing this on and on again over the scan, we are tracking the motion of the subject. And the nice thing about the runtime control is that we have a linear model, and the runtime control that we adapted the whole time keeps the current navigators close to the reference navigator, and that makes the linear model stay valid over time, although we have quite some time and motion passing. And there we end up with some results. So this is no instructed motion at 7 Tesla. Upper row, no motion correction. Lower row, bottom row, motion correction. They have a similar rigid parameter. So half a degree, half a millimeter that involuntarily happened. But you see at the interhemispheric fissure, like the difference, what the navigation method can do for us. So a few pros and cons. What the method can deliver is like high precision, single digit micrometer and millidegrees. We have short navigator acquisition, so they don't take long in the sequence, and there's a minimal on-the-fly calibration in sub-seconds. So this is pretty nice about the method. No hardware requirements, no workflow impact. You just start the scan and go. The bad things are basically bad things about navigators, like downsides. We are sequence dependent, so you need somebody who plugs it into your sequence. We are currently bound to 3D with a method, and we need a stable contrast for this method. And of course, as in every navigator method, things you don't model, but that happen, they distort and bias your outcome. And yeah, there are some effects that happen for large motion excursions, and they are limiting the range of the motion correction. We have done our work on Philips systems. Within our collaboration, we want to move to the Siemens platform for Paris, and with the help of the people from Bonn, especially Matthias Serger and Philipp Eses, like they did this great job of transferring it to the 70 Siemens platform. There was an abstract in the ISMRM that you see here, with the aim of bringing it to the 11.7, of course. Just as a quick side note, we also applied the servo navigation to 3D EPI fMRI, which I will be presenting in the open optimized acquisition and reconstruction session on Friday evening. Yeah, please pass by if you're interested in how we can improve voxel signal stability. So the next point is expansion to runtime gradient shimming. The idea here is in the scanner, we have effects like breathing, we have chest motion, we can have arm motion, system drifts. And these sources that are kind of external to the brain imaging realm, they can usually be captured well in low order spherical harmonics. And the shim coils of the scanners, they are tailored for this, like they are made for this kind of stuff. And we want to use them for runtime shim adaptation with the same method here to get the fields corrected in runtime as well. So we do the same thing, navigator signals, linear model, and updates. The things that we have to add now are 3 columns in the linear matrix, because we need to estimate these parameters and do the updates then. And we do it again by a finite differences calibration. So we measure 3 additional navigators in the initial referencing step in 3 TRs, where we just switch on the read, then the phase, and then the slice gradient by a tiny bit, like 5 microtesla per meter. Which is not so tiny, but anyways, but yeah, and we use finite differences to estimate the column again. Now we have the model extended and can use it, and that's what comes out. So we instructed arm motion at 3 Tesla. There's a reference on the left where no motion was happening. And now we ask the volunteer to move the right arm to the left shoulder in the middle of the scan. And without a motion correction, it looks like that. With a motion correction and F0 control, it looks like that. And with the gradient shimming, it looks like that. And if you have a closer look on the frontal lobe, you see that these shining effects are reduced with increasing field order that we correct for. And also that the gray-white matter continuity and integrity is much better and closer to the reference image. And that tells us that this method with first-order field control is capturing the field dynamics better than the previous method. A little look on the motion traces that we get out of our method. There's quite some physiology inside, and I'm always happy to look at this data. So on the left chart here, you see like a bunch of parameters and breathing belts and pulse oximeter. So the dark gray is a breathing belt. And when you look at some parameters like the Z shift, so the shift up, you see that the breathing is inside and also the Z gradient, so the field gradient in Z direction by the breathing is captured by this method. And when you high-pass filter the Z shift, and compare it to the pulse oximeter in light gray, you actually see like that the spikes coincide pretty well between, like you have to imagine that it's the blood entering the finger measured by the pulse oximeter, which we capture like also in the Z shifts, that the head is bumping up by 50 to 100 micrometer due to cardioballistic effects. And this method and this data contains these kind of information, which we are very happy to see also as a validation. So the last topic I would like to touch is post-dependent field-corrected image reconstructions. Like the motivation, like there's a really nice underlying study from NIH, from Leo et al. They were looking at the field variations in 70 with pose, like how much does it change? So they measured field maps in the reference position, and after several head rotations that you see here in the column, they even differentiated between magnetic field inhomogeneities that you move in and tissue-related susceptibility fields. The point I want to make here is that they also showed that they were looking at how well can these fields changes be represented in spherical harmonics. And so the question, are they shimmable? And the answer, like when you look here for the third order, it's basically over here, third order shimming, what many high field systems have. It's about half of the residual field that you capture with these kind of, with shimming. All the rest has such a high spatial complexity that you cannot get it with current coil systems. So in this method, the objective is to combine prospective and retrospective motion correction. So we use this servo navigation method for rigid correction, but also do a reconstruction method to further get these fields with higher spatial complexity. And the method overview, like we have a runtime part and a post-processing part. On the runtime part, we have the MR scan with prospective motion correction. We have the navigators inside, and we randomize the phase encoding for conditioning purposes. And on the post-processing side, we are then clustering after the scan the shots into motion clusters and apply a model to solve for the field terms at low resolution and plug them into a high resolution image reconstruction. So yeah, the disorder we are using to get a broad spatial temporal sampling of the field dynamics, because they are complex in both temporal and spatial dimension. That's why it's good. It gives us a better conditioning. And the second part I would like to talk about before showing you some results is post-dependent field and image reconstruction model. We adopt the linear coefficient map model by Sulikovska et al. That linearizes the field change per voxel with respect to the rotations against the main field, so roll and pitch, so that you split up your spatio-temporal field dynamics into two maps that just depend on space, and the rotations, and those rotations we get from the navigation methods. The others we have to estimate what we do in B-splines. We do this by a sense-based alternating reconstruction for the image raw and the B-spline coefficients. Due to time reasons, I don't want to go into more detail on this model. Please contact me if you're interested in it. I'm happy to talk about it. So we have the model in place now. We have the sampling in place. We did some scans at 7 Tesla with relatively high echo times of 28 milliseconds without instructed motion and with instructed motion, where we asked them to perform a series of take a series of positions, and these are the artifacts you're getting from that, like signal dropouts and like these wave-like artifacts above the nasal cavities because of the field inconsistencies over there. And applying the post-dependent field corrections by our algorithm, you see that these artifacts, they are tremendously mitigated. And the nice thing is you also see in the no instructed motion case, you see quite some changes that gives you also higher gray matter continuity, for example. If you look at it, like this contrast is just very sensitive at high field to motion, even tiny motion. And that brings me to wrap up. We've looked into the servo navigation approach with all its advantages, and we looked into the field dynamics, into an expansion to runtime gradient shimming and retrospective post-dependent field estimations and corrections. And I'm very happy to move forward with this, seeing all these things like the magnet, the coils, the PTX, the motion correction coming together in Paris. And of course, we are working on improving the navigator and what it can provide. And I want to say a big thank you to my team in Zurich and also to the AROMA project, to all of you guys. It's a nice collaboration. I'm thankful for the funding and the nice time we have and the interesting projects. Thank you very much. I'm happy to take questions.
Yeah, thank you very much, Malte, for that great talk and showing on the progress you've been able to achieve with actually navigator-based correction without any external tracking devices, mind you, right? I mean, leaving aside the limitations, it's actually quite promising to see what you can do with minimal extra scan time. Questions? I see one's lined up already.
Yeah, great talk. Thank you. You've mentioned that there's a limited range of motion that you can you can detect and correct with servo navigators, but can you be a bit more specific about it? Like, have you tested like what is the reasonable range that this method works for?
What I can say about it, like, there's no general answer to your question because it depends on the setup you have, on the coil, on the field strength as well, etc. So I could not hand you over a number, something like that.
Well, yeah, I know there's no sharp boundary, but you know, like
we know that for sorry.
Yeah, no, I know there's no sharp boundary like that. It works up to like, I don't know, like this range of motion and then it stops. But like, is there like reasonable value, like in terms of rotations, for example?
So what we see is that we achieve like for that we can work. I would say in a range of 2 millimeters in degrees. Like things work fine. So when you have cooperative volunteers. This method works pretty well, like you have seen, like this works nicely. I guess when you come to pediatric applications or something like this, like we have to go on solving problems with a method like these unmodeled effects I was talking about. There needs to be progress to make them valuable for these applications as well. Yeah.
Great, thanks.
Welcome.
Any other questions for Malte on the motion correction talk? Well, again, I said there will be opportunity afterwards to talk to him, mind you, not least in the opening reception tonight. So with this let's move on to the last talk in the session after thanking Malte one more time.
Thank you.
And so next up, we will have Caroline Lester from Neurospin, who will give us an update on the current status on the 11.7.
Thank you for the introduction. So I'm going to present you the work we've been doing lately on ESULT and on behalf of all the ESULT team who has been working in Neurospin on this project. The presentation will be as follows. So first I'll talk about the journey to get the first in vivo human images at 11.7 Tesla. And first, how did we get from a magnet to a scanner? The idea of scanning in vivo humans at 11.7 Tesla originates from 2001 with Denis Le Bihan, and it was decided that it will be the CA who will build the magnet with the following specifications. Okay. There were a few years of research and prototyping, and then from 2010 to 2017, the magnet was manufactured in a factory in the east of France called Belfort. Then the magnet was delivered to Neurospin in 2017. For the next 2 years, the magnet was connected to the cryogenic plant, cooled, and the field was ramped up to 11.7 Tesla for the first time. The next year, Siemens brought its imaging equipment with the SE72 gradient, the RF cabinets, and the consoles. From 2020 to 2022, we led an intensive gradient magnet interaction campaign. I'll come back to that later. And in 2021, we were finally able to get the first ex vivo images on this scanner. So first on a pumpkin and then on an ex vivo brain. As I just told you, the imaging system is from Siemens. We have a transmit 32 receive RF chain. The gradient coil is the SE72 wall body gradient. And we have a Bezier scheme up to the second order. I'll come back to that later also. We currently have 2 PTX coils. The first one is called the ISOL coil. It's a homemade coil with 16 transceiver elements combined to 8 and 16 receive-only elements. It's compatible with our homemade B0 shim insert. Since the beginning of the year, we have also the AROMA coil that was designed by Shajan Gwanamoni from the University of Glasgow within the AROMA project. And it's compatible with field monitoring. As you can see, these 2 coils have a quite different design. The AROMA coil has a transmission part much further away from the head compared to ISOLT. Now I'll talk a bit about the scanner characterization. So it was an intensive test campaign that was led in order to know within which mode we can use the scanner without having any issue and how to get the best images. For this test, we took advantage of the fact that we can ramp up and down the scanner quite easily. And we made several tests with acoustic tests. We measured also the vibration by taping some accelerometers on different parts of the scanner, as shown on the picture. We measured also the energy deposition in the helium bath. And one of the tests that gave us the most information was the gradient transfer function. So in an ideal system would have an input equal to the output. So the transfer function should be equal to 1 for all of the axes, X, Y, and Z axis. But unfortunately, it's not the case. We see that the gradient acts as a low pass system. And what is important is to have a look at the peaks that we can observe on the 3 axes. And it's these peaks that will cause some problems on the images, especially the EPI images. And in the first time, we had put a LED tube around the gradient coil in order to screen the gradient magnet interactions and reduce the energy deposition in the helium bath. But after some time, we saw that it was causing really strong ghosting artifact on our EPI images. So it was decided to remove it. And you see on the transfer function, we can already see the improvement because we have much less peaks in the blue configuration compared to the red one. So it shows an improvement of image quality. So the improvement is for the X, Y, and Z axis, except for one resonance frequency for the Z axis at 1350 Hz. This 1350 Hz resonance is called the breathing mode of the scanner, and it's caused by a mechanical vibration of the gradient due to Lorentz force. And we are going to see here just a small example of why this is an issue. So if we consider an EPI with an infinite train, it can be decomposed into a Fourier series with the following equation. So it's a sum of sinuses with a fundamental frequency omega 0 that is equal to 1/2 times the echo spacing. And if we choose wildly the echo spacing to 0.37 milliseconds, then the fundamental frequency is equal to 1350 Hz. An echo spacing of 0.37 milliseconds is not so common in EPI protocols. But if we choose this time an echo spacing of 1.11 milliseconds, then the fundamental frequency is equal to 450 Hz, and the third harmonic of this EPI train is 1350 Hz. So this is a simulation of an EPI train with an echo spacing of 1.11 milliseconds. And if we look here in blue, this is the nominal gradient waveform we want to play. And in red here is when we will take back the peak here we have on our transfer function. So an amplification of 5% of the amplitude at 1350 Hz. It will lead to this kind of deformation of the gradient waveform. And if we also take into account the phase deformation, it leads to the yellow profile here. So this is quite a strong distortion of the EPI plateau. And it's something we wanted to correct for before getting some images. So we spent a lot of time trying to troubleshoot the scanner and find the origin of these strong peaks and the transfer function. And after some time, we finally found out that when we unplug the third-order shim coil on our scanner, we are able to reduce the peak amplitude, meaning less coupling between the gradient and the magnet, and an improved transfer function. This result was important because it's the case not only for ISOLT, but also for other systems. For instance, this result was obtained by Renzo Huber, and it's you can see it on his Layer fMRI blog, where he acquires the same EPI image with the same protocol, either with the third-order shim coil plugged or unplugged. And he showed that he's able to get rid of ripple artifacts on the EPI image when he unplugs the third-order shim. In parallel to improving the images obtained with the scanner, another milestone was to get the ethical approval to scan humans on ISOLT. So ISOLT is considered a medical device without a C label and without an intention to get one. So according to the medical device regulation, we had to perform a clinical investigation before having humans, before using it routinely. So many people in Eurospin were involved in these steps. There was a literature review, also some physiological studies to study the effect of B0 field on the inner ear of a mice, for instance. Also, the vital signs were measured on an anesthetized monkey during imaging, as you can see here. So it was the opportunity to get the first in vivo images on September 2022. We measured also the genotoxicity on human blood samples. And finally, we validated the ISOLT coil on a phantom. So with all this data, we provided them to the French authorities and we got the authorization to scan humans to launch the clinical investigation in February 2023. This clinical investigation was called the PREM studies. Its primary objective was the safety, to see the effect of such a high field on humans. And the secondary objective was to perform, of course, the first MR images on humans. So the volunteers underwent several tests, balance test, attention test. We measured their vital signs and the genotoxicity. The first batch of volunteers, we scanned them at 0 Tesla, so the field was not turned on. And we played a gradient-like noise in order to make a nocebo effect. And the next 20 volunteers were scanned with the field ramped up to 11.7 Tesla. The first image we obtained in July 2023, and the last subject we scanned in February of this year. So the PREM study, all the volunteers had a localizer, a delta B0 map, and a B1 plus map. They were used to design some tailored pulses for 2D or 3D sequences. Once we had acquired these maps on a few volunteers, Vincent Gras was able to design universal pulses for 2D or 3D sequences. Since we had so few volunteers to scan, the protocol was very iterative, changing over the subjects. You see here the installation of a subject with the radiographers. And now some images. So first, the 2D T2 star-weighted GRE. We acquired them with two different strategies. On the left, with two RF shims that are summed up to obtain one image using the TMO approach. So it's in plane resolution of 0.19 millimeter with slices of 1 millimeter. The acquisition time is 2 times 5 minutes. And then Vincent Gras was able to design a 2D metapulse, and the acquisition time was reduced to 5 minutes to get this image. Here is just a zoom where we can appreciate the anatomical details. We also acquired the 3D T2 star-rated slab-selective GRE sequences with the resolution given here in a scan time of 11 minutes 30 seconds. Here again, we can appreciate the nice anatomical details. We acquired also some 3D T2 weighted space sequences with an isotropic resolution of 0.55 millimeter and an acquisition time of 13 minutes. So to conclude on the PREM study, its primary objective, as I told you, was the safety. I didn't detail it in this presentation, but you can find more information on this paper. So we didn't detect any harmful effect on the cohort of 20 subjects scanned at 11.7 Tesla. And we didn't find any difference between the subjects scanned at 0 Tesla and 11.7 Tesla. Regarding the imaging, we were happy to obtain high contrast and high resolution images in a limited scan time. The motion was highly challenging on our images because of discomfort in the coil and the high scan time. And also there was some challenges to obtain some pulses, for instance, the inversion pulses for the MPRH sequence. Now, the current status of ESULT. So for now, we were able to scan only 20 volunteers, the one of the PREM study. We are waiting now for an IRB approval to start new studies. This is because of an internal process that is taking some time. So we expect to have the authorization to scan again this winter. As I just told you, the motion is an issue. So we are using the 3D sequence that has been enabled for prospective motion correction using the approach described by Malte in the previous talk. We also implemented the FAT-NAV strategy that will be tested once we can scan again. We plan also to compare two strategies to acquire data. The first one is to use the ESULT coil with a B0 shim insert. You see here some data from the 70. The B0 shim insert is supposed to reduce the delta B0 inhomogeneities in the brain. So on the EPA images, it will lead to a reduction of the distortion artifact and a retrieve signal in the synesis and temporal lobes. The second approach is to use the AROMA coil. So it's this shape here, and the housing of the coil can host the field monitoring probes that were designed also within the framework of the AROMA project. So we will compare these two strategies, and what we think is that which coil to use with either B0 shim insert or field monitoring. It will depend on the scientific question we have. We are also getting ready for fMRI studies. For now, we have only the 3D PI sequence available. We were able to test it on a few subjects of the PREMS cohort. You see the images here at different resolutions. We were quite happy with the results. So it looks encouraging. And our protocols for fMRI experiments will be strongly limited by the physiology. So the SAR levels will be, of course, a limitation because of the RF heating. Also, the acoustic noise of the sequence will have to be measured, either not to be too loud. And the susceptibility artifact that increase with the field also will be a limitation. As I've mentioned, we still have an issue with the 1350 Hz resonance. So we decided not to scan at this frequency for the fMRI protocols. So this frequency will add up to the forbidden frequencies of the SE72 gradient. And in the end, it's quite a lot of frequency we can't use for fMRI. So this, of course, will have to be, we have to find a way to have some nice protocols for API imaging. So we have all these challenges to overcome, but then we plan to have a long scientific journey ahead of us with first some cognitive neuroscience studies. We plan also to have some studies on the pathological conditions of the brain. The first study will be on Parkinson's disease and multiple sclerosis. And I didn't mention it in this presentation, but of course, X-nuclear imaging will be an application of a real interest for ESULT exploitation. And with that, I thank you for your attention. Thank you.
Yeah, thanks, Caroline, for this update from Neurospin and where you're at with the 11.7. Are there any questions for her? No questions? I think in the interest of time, we might then as well call this a wrap. Let's thank Caroline one more time. And of course, all the other speakers in the session as well, Rüdiger, who's not back yet, Theodor and Malte. And of course, to all of you here for sharing your interest in the AROMA project. There will, of course, be opportunity to catch us here in the coming days at the reception later or during the break now. And thanks again all for coming. And this is it from Tony and myself. Thank you.
Thank you.